Okay, section 15.7 is on page 941, talks about triple integrals in cylindrical and spherical coordinates. Now, I am going to break this into 2 lectures as well. You know, I'm going to pretend that I'm in class. If I was in class, I would have finished 15.5, the rest of it. And I would have started 15.7, but maybe not being able to finish it. So I'm going to do half of it today, which is cylindrical coordinates. And those are the ones we're used to from our math 1150, the previous semester. Spherical is something new. We'll talk about that next class meeting. So let me just adjust this a bit. Here we go. So the way it works, we define, instead of x, y, and z, well, z remains z. What that means, we don't change z. But instead of x and y, we call them r and theta. And if you remember how that game was played, r squared equal x squared plus y squared, tan of theta equals y over x, and x equal r times the cosine of theta, and y equal r times the sine of theta. There it is. And that's pretty much what the section is about. To really plot a point, it would look like this. So if you want to take a point in the xyz plane and make it into r, theta, and z, well, guess what? Now here they restrict r to be always positive, which makes our life a lot easier. So if you want to go to a specific location, what you do, remember, r, theta, and z. Well, instead of moving left and right, you rotate first. If r is positive, in this case, r is always more positive. You move r, and then from that point, z is the same. Z is simply going up or down. And the way cylindrical coordinates come from, if I take this graph that I just introduced, let me do it again. The name cylindrical coordinates comes from, if you let this point right here, right, if you let r and theta rotate freely any way you want, well, wouldn't that create like a circular pattern? And if you have z run up and down freely, think about it. Wouldn't that create a cylinder? So if I have r being fixed, theta runs all around, creating this circle. And if I have z run up and down with a circle, wouldn't that actually create the actual disk? The actual cylinder, and that's where the cylindrical coordinates come from. If I was in class, I could show you that with ease. Well, what do we have to do? We have to get used to this first. That is, we have to get used to this 3 dimensions, and the first batch of problems, which is the only thing I want to cover today, really talks about sketching a graph. Nothing yet. Well, keep in mind, graphing is literally half of the problem. Not the actual graph per se, but you being able to visualize what the graph looks like. Sketch the graph described by the following cylindrical coordinates in 3 dimensions, and let's talk about this. So, this is what we do. We run back to 1150. We did those plus. So we did those, and we did more actually than what this section has. This is on page 949 in our book. So if I get the 3 dimensions on, I'll notice that, you know what? Oops, the other 3 dimensions, right? This. Well, keep in mind how this game is played. Theta equal pi over 4 is a line. Remember? You rotate to pi over 4, and since there's no r, it takes on all the values. That's an infinite amount of values. Well, a bit hard to draw here. This should be a line cutting but r is positive, right? So here r could be positive or negative. That's where the line comes from. If r is only allowed to be positive, then you only get that piece. This is a line, but since there's no z is not present, then if you let red z run up and down, guess what you'll get? A plane. Z equal r. Well, let's see. There is no theta. That means theta could run all what theta does, it rotates. It's going to keep rotating non-stop. If I take the 3D, so here, if you say r equals 0, z equals 0. If you say r equal 1, z equal 1. Okay. R equal 1, there's 1, and z equal 1, that's 1. They're going to meet right there. But theta is going to rotate all around. If you say r equal 2, then z will equal 2, and they meet right there. But theta will run all around. And do you see that if theta equal a half and r equal a half, do you see what you're creating? You end up creating a cone. Right? Remember, r squared is x squared plus y squared. So those are a bunch of circles, but z equal that. They're matching. So you end up with really something like this. If you have any questions on this, you're welcome to ask me again in the discussion when we get there. That's after the exam on Friday, since next class meeting is a review for us. Okay. And number 6, r sine of theta. Hey, isn't that a y? Right? Oh, come on. Isn't that y? Wouldn't that be z equal y? Isn't z equal y cutting this at 45 degrees? But there's a catch. R is always positive, which means I can go in the negative direction. Z is always positive. Since there's no x, isn't that going to be wrapped around the x-axis? At 45 degrees. And one more. I could do the rest, but they're going to come up in different problems, so there's no point in prolonging this. Let me just match this. Let me move it a bit to the left. Come on. Oh, here we go. What do you know? Put this way. If I get number 8 right up there. Now, can you guess what this is? We did. If you say r is between 1 and 2, there it is. So you're talking about sort of this region. And if you say theta is going to run from 0 to pi over 3, you are only talking about what? Only that region. True? Well, let's remember that here. R equal 1. There's R equal 1. R equal 2. We're talking about this region. And it's cut out by 0 and pi over 3, roughly 60 degrees. But do you see there's no z? Doesn't that mean this is going to mimic, it's going to run infinite? So again, it looks like I'm doing just a portion of it, but no, in reality it's infinity. All the way up, all the way down. This thing is never going to terminate. But it looks like that. Okay, let me get spherical coordinates started. Again, you're not going to get much on it. I just want to introduce it just so that you'll have a feel of what's to come. So, spherical coordinates are slightly different in the sense I'll go over that again next time, but it's good to see this twice. It takes a bit until it sticks in. In class, I would move my arms and show you a few things. Here, it's kind of hard to do since I'm going to stand there and embarrass myself. I won't. So spherical coordinates really turns out to be two angles and one fixed length. So one of them you already know, and hopefully you're comfortable with, and here it is. That's theta. Theta is the same traditional theta that you are familiar with. So this is the same. Rho is fixed. Rho is an actual distance. So you fix this one distance. You have one fixed length. Theta runs on the floor. So theta runs, circulate up and down. Phi has a condition. Phi can only be between 0 and pi, and not only that, phi equals 0 is really pointing on the positive z-axis, and it starts moving downwards. So think of it this way. A fire truck, right? A fire truck gets to a building. They have the ladder. Assume the ladder is standing up, not, normally the ladder is flat on top of the truck. Assume the ladder is standing up. It's really vertical, right? That's where it starts. So one thing you have to do, you have to rotate until you are lined up with the building. Assume the building's right there. And this is the window you want to reach. So the ladder starts right there. One thing you want to do, you want to rotate, you want to turn until the actual ladder where people are going to come out matches the window. Then what you want to do, you want to drop it down until it matches the window. So this is phi. You drop it, first you rotate it until this part in which people are going to step on lines up with the window. Then you need to drop it down until it lines up with the window, and you need to stretch it out. You need the ladder to stretch out until it reaches the window. So three things must happen. This must line up correctly, that angle must be right, and that length must be correct. Right? So assume when you start at 0, this ladder is always pointing in the x direction. You gotta start rotating that until it matches where the building is. So if the building happened to be on the y-axis, right? And you're starting right there every time, you're gonna have to rotate first. You're gonna have to rotate first 90 degrees. Now the ladder is matching the z-axis, the y-axis. Then you need to drop it. Let's say it's right there. You need to drop it until it lines up with that specific angle, whatever that is. Let's say it's 45 degrees. And then you need rho. You need this distance to match so that you could reach that one window. I'll talk about that next time. Again, the idea is kind of confusing. Excuse me. I'll derive some formulas. It's not corona. We'll derive some formulas and we go from there. I'm gonna add the homework for you. And here's your homework. And on the next lecture, so I'm breaking those lectures. I'm gonna post this up tomorrow. That's for Friday, but we'll talk about that when we get there. So the second half will be probably after spring break.